Hello, everyone, and welcome to today's media briefing for NASA's James Webb Space Telescope. My name is Elise Fisher. I'm with NASA's Office of Communications, and thank you very much to everyone who has joined us today, both on the phone and here in the room at the Space Telescope Science Institute in Baltimore, where Webb's Mission Operations Center is located. In just about 2 weeks, on July 12th, with our partners, the European Space Agency and the Canadian Space Agency, NASA will release Webb's very first full-color images and spectroscopic data. But before we get there, the team is completing the final weeks of a month-long process of preparing Webb for its science mission. So you'll hear more about that today. So to begin, I am very pleased to welcome for some opening remarks on the phone, NASA Administrator Bill Nelson, as well as here in the room, NASA Deputy Administrator Pam Melroy, and NASA's Associate Administrator for the Science Mission Directorate, Thomas Serbuchen. So we will hear brief remarks from each of them. We will have an opportunity for short Q&A, and then we will move on to our other panels today to hear a bit more about Webb science and the observatory. So to begin, I will turn it over to Administrator Nelson.
Good morning. I wish I could be there, but I tested positive for COVID last night. This is obviously a time I wanted to be there because we're in the final countdown to July 12th. We're going to give humanity a new view of the cosmos, and it's a view that we've never seen before. So shortly, we're going to be seeing the first images from JWST. And that's because Webb is nothing short of a real scientific feat. Now, we have some news to share with you. One of those images on July 12th is the deepest image of our universe that has ever been taken. If you think about that, this is farther than humanity has ever looked before. And we're only beginning to understand what Webb can and will do. It's going to explore objects in the solar system and atmospheres of exoplanets orbiting other stars, giving us a clue as to whether potentially their atmospheres are similar to our own. It may answer some questions that we have. Where do we come from? What more is out there? Who are we? And of course, it's going to answer some questions that we don't even know what the questions are. So in many ways, Webb's journey is only just begun. Our Deputy Administrator, Pam Melroy, is going to share more about that in a moment. So you're going to meet the Webb team today, the individuals who made this moment possible. And it is a team, and it was led by Greg Robinson, director of the James Webb Space Telescope program. By the way, he's a finalist for the 2022 Sam Heyman Service to America Medal, which is otherwise known as the Sammys. And Greg's leadership has helped us get to where we are today. But Greg is going to be the first to give the credit to everybody else, to the engineers, the scientists, the leaders who have poured their life's passion into this project. And he's right. It's been an extraordinary team. So coming up shortly, July 12th, we're going to see a major result of their work, and it is going to be in full bloom all the work of their labors come to fruition. And you'll see on that date what everybody is so excited about. Now, I want to introduce my co-leader, our deputy administrator, Pam Melroy. She is a visionary in her own right, a former astronaut commander, a former test pilot. She and Bob Cabana have been great partners as we try to offer some leadership to NASA. Pam?
Thank you, Bill. I sure wish you could be here, Mr. Administrator, because this is the beating heartbeat of Hubble, James Webb, and in the future, Nancy Grace Roman. And I wish you could feel the energy that I feel in the building and in the room. We're just so excited, as you pointed out, that we're in the final countdown. I also want to reiterate your congratulations to Greg Robinson and his team, everyone at Goddard and here at the Space Telescope Science Institute, our industry partners, Northrop Grumman and Ball Aerospace, and of course, our international partners as well, the European Space Agency and the Canadian Space Agency. This is a very exciting moment. We cannot wait to get that data. We know that it is going to, as Ken said, force us to rewrite the textbooks again. And I just want to point out it's a great example of what the government can do in science. Make these kinds of major investments, these huge challenges that will not just inspire, but help us understand ourselves and the universe better. And the world has followed us every step of the way. One of the things that I'm proudest about is that under Thomas's leadership, we have exposed both the risk and the excitement and the drama, but most of all the uncertainty that happens as a part of the scientific process, and then the joy in learning and overcoming challenges and successes. So along with Bill's news about the first images, I am very happy to report that our estimates of the excess fuel capability of Webb have proven to be correct. So thanks to our partners at Arianespace, who did a perfect job of inserting Webb into space with a very high level of precision, we can confirm we have 20 years of science data capability with the propellant that we have on board. From a personal standpoint, I'm very excited about that for a couple of different reasons. One, of course, is simply that we will be able to do more cutting-edge science. But I'd like to point out that as a part of the scientific process, we learn a lot, and then data is published. People think about it. They go back. They start another process. We have some of those questions we don't know the answers to. We see the answers, and then we develop more science to help go deeper. So not only will those 20 years allow us to go deeper into history and time, but we will go deeper into the science because we have the opportunity to learn and grow and make new observations. So that's very exciting. And you're going to hear a lot more about that from the team today. So I just want to point out that this mission is going to be at the very center of NASA's astrophysics mission for 2 decades to come. And I'd like to turn it over now to our Associate Administrator for the Science Mission Directorate, Dr. Thomas Zurbuchen.
Well, thanks so much. So excited to be here with you and the Administrator. We, of course, talk about Webb all the time and about science missions in a broader sense. And I really want to echo the words that you said and what the Administrator said, really giving credit to the amazing team that got us here. And one of the most important things in science is to figure out what's a conserved quantity and what's not a conserved quantity. I want to tell you that credit is not a conserved quantity, so everybody can take 100% of it. And so let me give 100% of credit to some other people who are here also. Bill Oakes, who's sitting there, who's going to talk to you later, of course, is the manager. And frankly, when I joined NASA and after me, Greg joined, the Webb program, he was already there and had built a team that was marching towards this. And we've had many challenges. I just want you to know we've been in many meetings that, frankly, took some of my night sleep afterwards. Many meetings, of course, that gave me that sleep back later. That I was actually not, expecting. And, frankly, the team that he and Scott Willoughby, who is not here right now, but is the manager at Northrop Grumman, I just want to tell you how much I appreciate their dedication and their eyes being locked on the prize each and every day, frankly, even if disappointments at times try to pull them away from that. So I just really wanted to do that, Bill. It's just been an honor working with you and observing you and Scott and the entire team. I'm going to single you out. We all know that when we talk about individuals, we really talk about teams that stand behind them. And, that the unit of success in these things is not a person, it's a team. So I really appreciate that. The first time I figured out something that nobody knew is a moment I'll never forget. It was 2 a.m. Yes, I used to work late as a grad student, still at times, but as a grad student, normally I work late. And I was in front of my computer screen, and I looked at something, data analysis that I had done, and something was absolutely clear to me looking at these data, correlation nobody had ever seen, that indicated the origin of specific streams of solar wind that I had looked at with new data, and that was like jumping out of the screen. And I remember how I felt that day. Research is an incredible activity, one of the most important activities of humans, because that moment how important it is as humans to broaden that space of knowledge, that space of understanding, the space we live and think in. And I felt that little piece of information really did that. I believe July 12th, for so many of us, not just for the researchers, but for all of us, will be that sense. I remember how close to tears I was that moment, because it's an emotional moment when you see nature suddenly releasing some of its secrets. And I would like you to just imagine and kind of look forward to that. No, it's not an image. It's a new world view that you're going to see. Nature giving up secrets that have been there for many decades, centuries, millennia, forever, for where we are as humans. So, of course, the path to that has been that amazing launch that Christmas morning. I don't know, last year we launched every holiday or the day before. My family is what the heck, dark before Thanksgiving and then on Christmas and, but the milestones since then, what has happened since then is just absolutely stunning to me. Bill, I don't think any of us expected how well it went. I don't know about you. I did not expect. You should answer the question later in front of people, but look, so we're getting to July 12th, and just in analogy of our colleagues here, what I would like to announce today is that I can confirm that's part of the July 12th release. We will share Webb's first exoplanet spectrum. So right from the beginning, we'll look at these worlds out there that, again, keep us awake at night as we look into the starry sky and wonder, as we're looking out there, is there life elsewhere? What are these worlds out there? We have 5,000 plus of that we have identified, and one of them will have a spectrum available on July 12th. You'll hear more later in the briefing, but that kind of overall kind of release of this kind of current to a new space of understanding is really right ahead of us. Again, as we do so, we look back at the many people who have got us there over 20 years. I want to tell you when I was here the last release, that final side mirror kind of release. I was here, and I spent the whole evening calling people. Everybody was in leadership positions. Everybody who had a managing position before, because it's just like a good race. These races, you go around the loop 4 times, and the last person gets over the finish line. But the only way they got there is by everybody doing their work. And so I just want to give credit to all of those as we go forward. So with that, Elise, I'm going to kick it back to you. Thanks so much.
Great. Well, thank you. And thank you all so much for those remarks. And as mentioned, we'll now pause to just take some questions. So for the sake of time here, we'd ask that you limit yourself to just one question. And please let us know which of our speakers you'd like to direct your question to. On the phone, you will be able to press *1 if you'd like to ask a question, but we will first start by taking questions in the room, and we will have a mic that will be passed around for questions. So we can start in room.
Issam Ahmed, AFP. For Dr. Thomas Uburkan, could you tell us a little bit more about the exoplanet spectrum, what exactly that means, what that might reveal, just a little bit of a clue on that?
And I just want to tell you that there's going to be some scientists who are a lot better than I am behind me also. But what's really unique about this capability we have is in the infrared and kind of, in that range to really see emissions as a function of kind of frequency, as color in the light. You say, why does that matter? Well, it turns out a lot of these small molecules that we're looking at, whether it's, CO2, what we're breathing out, or it's ozone, they all have vibrational spectrum. So they kind of vibrate in the atmosphere. And so, and they just happen, those vibrational spectra happen to be, are in the range that we're looking at to a large extent. So you say, why would we care about it? So in other words, there's fingerprints of these kind of small molecules, these specific molecules there. Well, we're excited about that is because we know that, of course, atmospheres reflect both the make of the exoplanet, but what's really exciting in our minds is that we know on Earth, for example, the atmosphere really changed when life arose. What I'm talking about is bacterial life arose here. Kind of much of the atmosphere has been shaped by that. CO2, for example, is an important component. Many of the oxygen components, there's papers that say that even nitrogen, which is an important part, actually has a lot to do with life here. So we're looking forward to seeing the atmosphere of that specific planet, but of many more because of all those. We are learning more about that planets in a ways that we've never seen before, but also because we'd like to see whether the atmospheres actually reflect the ability of a given planet to kind of potentially, in our minds, in our models, harbor, or be a space where life can evolve.
Thank you. We can take our next question in room. Go ahead.
Good morning, and thank you for this day, and congratulations to the entire team. Greg Redfern, WTOP Radio. And the question that's really been on my mind is, who decided and what was the process of what pictures were to be released on July 12th? That's really been my burning question. And thank you.
What I'm going to do is give an answer, and I'm going to ask Ken, if I get it wrong, to walk up there and correct me. You good with that? So actually, the way we did this is not top-down, but bottoms-up. And we basically asked the team to basically come up with a series, kind of, I think of it like a dessert buffet, right? Kind of a series of kind of measurements that would really kind of represent the best what this capability can offer without kind of staying away from certain things. Like, for example, we don't want to undercut a lot of the science that's already proposed kind of later on, but really that team kind of decided on the targets that are there in a specific fashion. And frankly, it came to me afterwards. So I just want you to know it's kind of from the people who are close to the instruments, the people that are close to the measurements. Who ultimately decided, Ken? You kind of stand up and say if you care. It was not me.
ultimately, again, it's somewhat of a collective decision. Eric Smith certainly has a hand in that. You and the NASA administration have a hand in that. And of course, we here at the Institute and the project also talk about that. So it's a bit of a collective effort, but you're right in saying that it was a bottoms-up effort rather than top-down.
So my contribution was great. That's the by the way, that happens to be my contribution in many questions. So.
Okay, another question in room.
Nadia Drake, National Geographic. This question I think is for Thomas, and I'm wondering, we've heard there's going to be a deep field and an exoplanet spectrum, but will you be releasing a specific list of targets before July 12th?
It's actually funny. This morning, I had a discussion with many of our colleagues, including our comms lead, Mark Etkind. Where are you, Mark? Perhaps he's. Oh, there you are. And ultimately, I want to make sure that we're aligned, but we really want to consider doing that. Perhaps under embargo before we go forward. Ultimately, I want to make sure that we're on the same page. And the major reason for that, I think a number of journalists have told us that they can prepare better for that release and make it more meaty of a story by doing that. So we want to consider it. Don't want to make a commitment right now at this moment in time. But I think the points that the journalists have brought forward make sense to us. We want you to be able to write the best stories that day. We're not going to release the pictures before. I just want to take that off the table. So because the picture is the story here. But, as you correctly say, some of these exoplanets, there's some, like the exoplanet, for example, that I talked about, there's stuff known about it, and you should be able to look up in the literature and elsewhere what's there. Perhaps look at pictures from other telescopes that you can go fish out of archives, so you can get a sense for a given environment. I like the suggestion.
Hi, I'm Rebecca from Space.com. My question is, you, I think, mentioned that along the course of, the development and the deployment of this mission, there were some sort of nerve-wracking moments, and I know it's we've all been holding our breath over the last 6 months, particularly as the telescope deploys. For you both, were there sort of particular nerve-wracking moments that stick out in your mind, either during the planning and development of the mission or during the deployment?
Yeah, let's ask Bill.
Yeah. Bill, you want to go ahead and, I think we all shared some of them together, but Bill, do you want to answer that?
Yeah, I usually don't have to have a microphone, but okay. No, there were, obviously during deployments, that was the most nerve-wracking. Thomas joked before about, asked me about confidence levels, and back, I guess Greg and I were interviewed on 60 Minutes. When I got asked about confidence, I said I was 100% confident. And I knew that because of the testing that we had done, the people that we had been involved. Now, if you would ask me, would it have gone 100% smooth? That's a different question, and I would have said no. We would have had some issues in there. We probably would have had to take a pause and work on things. But it has been. I'm stealing some of my thunder from my panel later, but it has been an amazing 6 months. And yeah, there were nerve-wracking times, but when you have a confidence in your team, then you can get through those very nervous times.
Hey, Thomas, this is the other Bill that's present today. I just want to point out it's extraordinary when once the Ariane 5 put it in a perfect position on a trajectory, and then you have 244 things that have to work perfectly, and all of them work perfectly. That's just extraordinary, and a great credit to the team that you all are hearing from today. There's one other that was a moment of question that ought to be recognized. And because Webb was running out of money, there was some consideration in the Congress of canceling it. But Senator Barbara Mikulski of Maryland, a key position on the Appropriations Committee, that as chair of that subcommittee overseeing NASA, was able to come to the rescue. So let's give credit where credit is due.
So if I answer the question, it's kind of what are my top three kind of worrisome moments, right? The first one was roughly a year into, well, in 2018 or so, where we really recognized that there were some mistakes that were occurring. And this has been talked about. There's nothing new to add. I just want you to know it's really hard to keep a team kind of at the level of excellence for many, many years and kind of make sure that the culture really stays like the team is today. This is really, really hard to do. And also there, kind of we had to do congressional briefings and so forth. We were flirting again with some bad outcomes. So for me, that was number one. I think number two for me, must have been, kind of as we were going through testing, there's, 2 to 3 times. None of them were really fatal. I always ask Bill Oakes. Hey, if this happened in space, would the telescope work? In most cases, it would have been fine, but reduced something, right? And so for me, that was kind of reassuring. But nonetheless, we had to redesign some parts. We had to redesign some systems. And for me, that some of these moments, right, were probably the number 2. And I think at the number 3 was really when we were at the launch site, right, where I always tell everybody, it's really hard to work on a $10 billion mission. Most people have never done it. It's a different way of work because there are no small problems. And so basically what happens, some glitches that would normally, was funny because we had other launches. The same things happened with small spacecraft, and we turn it around in hours, on these bigger spacecraft, not because anybody did anything violently bad. It just hiccups. We again talked about those, with the clamp and with issues like that. We talked about these. That was probably the 3rd time, just because you kind of the worst, the biggest disappointment is if you're like in a race, as you fall on your face before a finish line, right? So for me, those kind of on the ground, those were the 3. Frankly, in space, there were times, and I always called either Menzel or Feinberg, right? It's like, hey, how much should I worry? It's like, don't worry too much, or hey, you should really worry about that more, right? So I get it. Sometimes it's hard, in a complex system to really know what's bold-faced and what's not. Kind of like of all the issues that are there, some of them are just issues, some of them are like, hey, problems in waiting. So for me, those are the 3.
Thank you. I'd like to make sure that we also have time to take a question or two from the phone lines. So we'll go to our operator quickly on the phone to take a question there.
Absolutely. Our first question is going to come from Eric Berger. Eric, your line is open.
Hi, thanks for doing this. First of all, I wish Administrator Nelson a quick recovery from COVID. And second, in terms of these images, have these already been taken, or what is the plan to do these observations over the next couple of weeks? I'd just love to know sort of if you have completed commissioning of the scientific instruments and have moved into observational mode, or when that's going to happen. Thanks very much.
So the images are being taken right now. There's a number of images that have already been taken. There's images, I want to make sure that when you think about images, we really think of data products. In some of the cases, there's multiple instruments that are involved in getting these data products. So some pieces may have been taken, some others have not. But yes, there's already some amazing science in the can. And some others are yet to be taken as we go forward. So we're right I would say we're in the middle of really getting the the history-making data down. We're not at the other end yet. Frankly, we're going to take some of these measurements until just days before the 12th, and you should be aware there may be some last-minute choices that we like. Hey, of the things we're doing, which ones are we going to put out? Right? Remember, that first release is just the first release. You'll be in many more press conferences about this telescope, and the most important ones, scientifically, surely will take a little bit of time to simmer over as we look at these amazing images. So you're in the middle, Eric.
Thank you. We'll take one more from the phone, and then I know we have one in the room as well, and then we'll have to wrap it up for this segment, but we can go ahead to the next phone question.
Our next question comes from Bill Harwood of CBS News. Bill, your line is open.
Hey, thank you very much. And I'm not sure who this is for, but I'm wondering how many data products, whether that's pictures or spectra, that we might see on 712. Maybe a ballpark thing. And secondly, very quickly, we're all familiar with Hubble deep fields and how many orbits it took to gather those photons. Can you give us a sense of how the image you're going to show us on the 12th, and I know you don't want to tell us too much about it, but is this something that was just a couple of orbits? Was it a lot of orbits? I'm just wondering how to put it in the context of the deep fields we're familiar with. Thanks.
Is there a science panel after us?
Yes, absolutely. So in our following panel, we'll get much more into those questions in particular.
So the short answer, one of the things I want to tell you, Bill, with this telescope, it's really hard not to break records. It's really hard not to break records. So kind of almost any time we looked at the universe, I remember standing in a room with Ken Sempak, who's the director here, and looking at a picture and say, this was not supposed to break a record. It already did. The ultra deep field of Hubble, right? That record, even kind of with engineering data, is already shaky, right? Or perhaps broken. My point is, it's really looking at the depth, and the administrator announced it correctly. The deepest image error will be there, and so just imagine that. I think there's, if I remember correctly, there's 10 or 20 kind of overall images and products that we looked at. A ratio, a fraction of it will be released. But I really would like to defer to the next panel because they're down and in on it, as opposed to me kind of getting beyond my two questions deep that I usually get.
Thank you. And we can go ahead and take our final question here in the room, and then we will have to wrap it up for this segment here.
Thank you so much. Kristen Fisher with CNN, and I guess this question is really for both of you. I know you say that some of these images are still being taken, some have already been taken, but can you just provide a bit of clarity on, have the two of you actually seen some of these images that are going to be released on July 12th? And if so, what did you think when you first saw them?
Oh, yeah, of course. I mean, come on, right? Yeah, actually, it's been a wonderful experience over the last 6 months. I know that when Thomas shows up in front of the administrator's office with a sheaf of papers and images in his hand, that something exciting is about to happen. So as we went through, you may remember that wonderful photo that showed each of the panels of the telescope with the star, reflected in it and then converged, and each step of the way, Thomas has brought things to us right away. I could not contain myself with just the limited, there's still some things being taken, but with what I have seen just moved me as a scientist, as an engineer, and as a human being.
Yeah, I think for me, so I saw a handful of those images, and for me, again, not all of them. I just really want to be clear, and it's not final. The teams are really working hard. I just want to acknowledge the hard work they're doing. But for me, looking at one of these images, frankly, I had the same feeling like that night, which is why I told you the story, because you really feel like the sky is opening up and you're in a moment in time and kind of space that you'll forever remember because you saw the universe like nobody has seen it yet. And billions will see it on the 12th. So I was kind of a sense of awe and frankly, got emotional, frankly. I asked Ken whether he had the same feeling, and he confirmed. So it's really hard to not look at the universe in new light and not just have a moment that is deeply personal in a way that, frankly, surprised me, I want to say.
All right, thank you both very much. So we will now be moving on to our next segment for this panel. So thank you so much to all of our speakers as well as to the administrator on the phone. We'll now pause and bring in our next panel here. Physics Division at NASA headquarters, Klaus Pontoppidan, Webb project scientist here at the Space Telescope Science Institute, Susan Mullally, Webb deputy project scientist, also at the Space Telescope Science Institute, and finally, Jonathan Gardner, deputy senior project scientist for Webb at NASA's Goddard Space Flight Center. So again, each of our speakers will share some brief remarks, and then we will take questions.
Yes, I'm going to lead off and talk a little bit more, I guess, kind of closer to the telescope, closer to the science, about what you all have heard was the reason that we built the Next Generation Space Telescope and now the James Webb Space Telescope.
Oh, sorry.
That was an argument. Yeah, that was an argument for servicing there, I think. So when we started this mission, it had its lead-in with discovering the first stars and galaxies in the universe. Now, how does that sound? Better? Okay. The initial goal for this mission was to see the first stars and galaxies. Not the first light of the universe, but to watch the universe turn the lights on for the first time. Of course, the other thing that we always knew that Webb would be is the general purpose telescope. And what you'll start to hear about today is the amazing array of things that this general purpose facility will be doing. Over the first year, there are 4 kinds of observations, broadly speaking, that it will be doing. You're here to learn about the early release observations or first light. That's a specific program with a specific goal, and Klaus will talk about that. We also have observations that will be conducted by scientists, the science team called the Science Working Group, who've been with us the whole time, developing the mission, and those observations, which were by design to be a little riskier for the telescope. These are the people that built the instruments. We really want them to push the telescope, and so they have observations in this first year. You will also hear about something called early release science. This is a program designed to get as much data from the telescope out to the community as quickly as possible. And so those will be some of the first observations executed as the mission starts. And the science community will be using those to help write better proposals for the second time. And then, of course, the bulk of the time goes to what is called the General Observer Program. And this is where people will be making incredible discoveries every day as they get their data from Webb. If I could, I'd like to relate just maybe, a couple of personal observations, because you'll hear a lot more about those science programs from my fellow panelists. recently there was an American Astronomical Society meeting in Pasadena. And of course, nobody had Webb data they could talk about there, but there were lots of people with posters and giving talks about what they would be doing with Webb. Many of those people weren't even in graduate school when the mission started, yet seeing their excitement, I mean, they were practically vibrating with excitement of what they were going to be doing with Webb. And that was just thrilling for me to see how ready they are to go. So we should probably start some informal pool about when the first paper shows up in the archive, because it will be hours, I think, and not days. The second thing I want to relate, this really isn't a science point, but for me, and this goes back to the engineering, the design of Webb, the way Webb looks, I think, is in large part another reason the public is really fascinated by this mission. It looks like a spaceship from the future, and we've realized that today, and very soon we're going to be realizing just what this mission can tell us. And I know I am really looking forward to seeing what all these young people will do with the telescope that we haven't thought of yet. And so with that, I am going to turn it over to Klaus to tell us a little bit more in detail about the early release observations.
All right. Thanks, Eric. I just want to start out with summarizing what the original purpose was of the first images, first color images, and the charter we had as a team. It was to demonstrate to the world that Webb is, in fact, ready for science, and that it produces excellent and spectacular results. And it's also to highlight the breadth, the sheer breadth of science that can be done with Webb, and to highlight all of the 4 science instruments. And last but not least, to celebrate the beginning of normal science operations, and as we've heard, many years of normal science operations. So this is a production that has been going on for a few weeks now with a team of absolutely amazing people, of experts. More than 30 of them have been working round the clock on this project so that we can deliver a fantastic package for release on July 12th. Now, we're still very much in the middle of producing this package. We're working every day. It's a complex process, right? It includes gathering, acquiring the data from the telescope, processing those data to a very high level of quality in a way that hasn't been done yet, and then assembling them into colorful images and other products. We're also very well aware that we're, in a real sense, we're sort of the first users of the observatory and using it for what it's built for. And in doing so, we recognize that we're standing on the shoulders of all the scientists and engineers who've worked hard for the past 6 months to make this possible. It's been a joy to use and a privilege to use the observatory. All right, so let me talk a little bit more about the content of the first images. We've already heard a couple of details. We will have a package that will consist of a number of full-color images. Each of them will reveal a different aspect of the infrared universe in unprecedented detail and sensitivity. We will also demonstrate how scientists will use the observatory to obtain spectroscopy, right? So this is a process where we split light into its individual colors to tell what things are made of and other properties. The first images, therefore, will include observations that span the range of Webb science themes. From the early universe, as we heard from the administrator, the deepest infrared view of the cosmos to date. In that context, so to me, what is also really exciting is that I know that this is not a record that will stand for very long. We know that scientists out in the world will very quickly beat our record and go even deeper. We'll also see an example of how galaxies interact and grow, and how these cataclysmic collisions between galaxies drive the process of star formation. process that happens in the universe to this day. We'll see a couple of examples from the life cycle of stars, starting from the birth of stars, where Webb can reveal new young stars emerging from their natal cloud of gas and dust, to the death of stars, like a dying star seeding the galaxy with new elements and new dust that may one day become part of new planetary systems. And then, of course, last but not least, as we heard, the first spectrum of an exoplanet. So I'm really looking forward to revealing these first color images to the world. But as others have said, I also want to emphasize that this is really only the beginning. We're only scratching the surface. We have in the first images a few days worth of observations. And looking forward, we have many years of observations, so we can only imagine what that will be. The next exciting phase is really to get the data out to the thousands of scientists around the world so they can dig into it. And then we can start a shared journey of discovery. So with that, I'll hand it over to Susan to talk more about the science.
Good morning, everybody. So we're now in the last couple weeks of commissioning. And if you've been keeping track, we're up to 13 of the 17 JWST's observing modes have been declared ready for science observations. So as those commissioning activities are tailing off, we're now able to bring in things like actual science observations. And some of the very first science observations have already been taken with the James Webb Space Telescope. In fact, the first ones were taken on the solstice, June 21st. These are being pulled from the Cycle 1 Science program, which was decided over a year ago now. This is a process where scientists from around the world proposed to use this telescope, and it was we had people from 44 different countries and 45 different U.S. states, including D.C. and the Virgin Islands, participate in this process. After they put in their proposals where they said, this is how I would use this observatory to answer the most interesting questions, what we can study with it, a panel of astronomers looked at that and picked out the best programs that would give us the most science. And the final program highlights all those themes that you just heard Klaus talk about. We have about a third of the program is going to observe galaxies and the intergalactic medium, the gas and dust that lies between the galaxies, with another 10% being used for active galaxies and studying the supermassive black holes that are at the center of them, with another small fraction to study cosmology and the expansion of the universe. But there's also programs within our own galaxy. 20% are going to work on stellar life cycles, showing us how stars were born and how they die. And along the theme of planetary science or planetary systems, about 5% are actually going to observe objects in our own solar system, looking at objects like Jupiter or Saturn or small objects even like comets. And then almost full quarter of the time that Webb has will be looking at exoplanets to study in particular their atmospheres or even how exoplanets are born in protoplanetary disks. So on July 12th, when you get to see the universe in a whole new light, scientists will also be looking at those images and trying to glean what they can do with this observatory and how they can use those images, or what we call data, to actually make precise measurements of planets, stars, and galaxies in our universe, and do it in a way that we've never been able to before. So I wanted to take a moment and just highlight some of the science programs that are especially interesting to me that are coming up over the next year that are available in that Cycle 1 Science program. So I'm a stellar and exoplanet scientist, so I'm going to keep my remarks to those objects that we're going to observe in our own galaxy. So along the themes of stellar life cycles, Webb is going to study a variety of stellar clusters. Stars are born out of clusters out of balls of gas and dust and fragment into individual stars. And Webb, for the first time, is going to allow us to see some of the smallest stars that form in these stellar clusters. These are red dwarf stars that we've never been able to see before.
we also are going to look at massive stars and how they produce massive stars that explode in supernova. But Webb, for the first time, is going to be able to look at the aftermath of really large explosions known as kilonova, where two neutron stars, stellar remnants, actually spiral in and collide, providing a way to produce some of the heaviest elements, common things that we see here on Earth, such as lead, silver, and gold. And then in the direction of planetary systems, Webb is going to give us our first insight into terrestrial planets, rocky planets like our own Earth. And in particular, there's an outstanding question of whether these terrestrial planets, which are orbiting small M-dwarf stars, can keep their atmospheres. Those M-dwarfs flare. They give out these high-energy flares, and we don't know if those atmospheres can survive that flaring star. And so with Webb, we will look to see if these terrestrial rocky planets have atmospheres at all, and if they do, are they anything like our atmosphere here on Earth? We'll also be looking at some hot rocky planets around other stars. And this gives us the opportunity to really look at geology of exoplanets. Because they're orbiting so close to their star, they likely don't have an atmosphere, and so the light will reflect off of the rocky surface, and we'll be able to actually look to see what kind of rocks are on that surface, and potentially also see if there's volcanism on the planet, doing geology on exoplanets that are tens of light years away. And now to talk about some of the extragalactic systems, we turn it over to Jonathan Gardner.
Thank you. I'd like to talk about the importance of interacting or merging galaxies that Klaus mentioned. One of the major science goals of Webb is to find the first galaxies that formed in the universe after the Big Bang. Webb can see backwards in time to just after the Big Bang by looking for galaxies that are so far away that the light has taken many billions of years to get from those galaxies to our telescope. Webb is bigger than Hubble so that it can see fainter galaxies that are further away. But we also expect that those first galaxies are intrinsically small, so they're extra faint, not just far away, but also faint themselves. Those first small, faint galaxies merge together again and again, building up over time to become the large spiral and elliptical galaxies that we see today, including spiral galaxies like our own home, the Milky Way. When galaxies collide, they don't go bang, they kind of go slosh. But because galaxies are mostly empty space, the stars themselves rarely collide with each other. But the gas does collide and can trigger bursts of star formation, forming the next generation within the final merged galaxy. Personally, I'm most excited about the deep surveys designed to find these distant galaxies. I have been working on deep fields since before Hubble launched in the 1980s when I was a graduate student using the telescopes in Hawaii. And I do mean surveys, plural. There's not just one. The Webb Cycle 1 astronomers have designed multiple surveys with a variety of depths and areas, whether going really deep in a single field of view or mapping out a bigger area in order to find the rare, brightest examples of each type of galaxies. The surveys will use NIRCam for the near-infrared imaging, MIRI for the mid-infrared, and NIRSpec and NIRISS to get spectra, which are the valuable data that tell us most conclusively how far away each galaxy is. These surveys will also use multiple colored filters. Remember that the July 12th images release will include the first color Webb data. The colors and spectra tell us about the elements in the stars in the galaxies, which in turn tells us whether the stars are first generation within the very earliest galaxies, or whether there has been a previous generation of stars and we need to look still further. The first images are exciting because they are the first science data that Webb will take. But this is just the beginning. On July 12th, we will feature the results of 120 hours of observations, 5 days of data. 5 days later, we'll have doubled Webb's output, and in the coming weeks and months, multiple additional results will spill out. The first year of Webb has been planned with proposals selected through peer-reviewed competition from scientists around the world. When those scientists get the data, they will process the images and spectra in their computers and puzzle out the new information. Some discoveries will come very quickly. Webb is powerful enough to make some new results obvious. Other discoveries will take more time as we push Webb and its instruments to the limits of their capabilities. Scientists will publish their results in the professional journals, but also the outreach team here at Space Telescope Science Institute will be putting out press releases and images based on the data and the discoveries to make those discoveries accessible to the public. We've just spent 6 months since launch doing the deployments, aligning the telescope, and checking out the instruments. The telescope is performing better than we expected with a sharper focus. Likewise, as we check out the instruments, they are also outperforming our requirements, which are the engineering criteria we wrote down years ago as needed to accomplish the science goals. The first images are going to be spectacular, but the science discoveries coming in the next year will be truly amazing. I'm personally excited about the deep field galaxy science, but I'm actually most excited about the surprises, the new things that we will learn that we don't yet know to expect.
Okay, thank you all so much. So again, we can go ahead and take questions here. Again, we'll start with those in the room and then move to the phone lines. But I would also like to note that in addition to our panelists here, if you have more specific questions about Webb Science instruments, their capabilities, their performance, as you've heard a little bit about that here, we do also have members of each instrument team available to address questions here as well. So on the phone lines, we have Renee Doyon, Principal Investigator for Canada's nearest instrument at the University of Montreal, as well as Kevin Hainline, member of the NIRCam science team at the University of Arizona. And then here in the room, we have Giovanna Giardino, European Space Agency NIRSpec scientist, and Yannis Argyriou, who is a mid-infrared instrument, or MIRI scientist with KU Leuven. So please feel free to direct questions to them as well, both on the phone and in the room, in addition to our panelists. And let's go ahead and get started with those in the room.
Hi, Jeff Faust of Space News. Just want to follow up on questions from the previous panel, and just in terms of how you assemble, this list of targets for the early release observations. Sounds like this is something of a dynamic process. Who's deciding, how is all this coming together, and who's deciding to take what images at what point? And then also quickly for Klaus, you mentioned that this is one of the images is going to be the deepest ever. Are you able to quantify that in terms of like redshift or some other metric?
All right, so yeah, I guess I can speak to both of those questions. So it's been a years-long process in coming up with what the first images would be. Originally, there was a small committee put down with representation from NASA, our partners, the European and Canadian Space Agencies and Space Telescope. And one of the challenges already back then we knew was that Webb can't see every part of the sky at any given time, and we didn't know when we were going to launch. So we knew that we needed a very long list of targets, I think it's more than 70 in the end that we had. And those were assembled with this charter in mind, right, to demonstrate the breadth of Webb science and to create spectacular color images. So they took inspiration from what Hubble had done, what Spitzer had done, what came before. And then this committee essentially prioritized this list in such a way that once we knew when we would be able to take the data, we could go down that prioritized list and take the highest prioritized targets that were visible at that time. That's sort of in very short. What was the second question?
About the deep field.
So I think an important point here about the first images is that we're just taking them. We can only scientifically not really have time to look at them in any detail at all. What will happen when the first images are released is that the next day the data themselves will also be released to the public and to the astronomical community. And so we expect scientists around the world to take them and analyze them in this way and look at, what are the redshifts and try to answer questions like that in detail.
Okay, great. Thank you. Do we have any other questions here in the room? Oh, one over here. Thank you.
Hi, this is Rebecca Soon from Space.com again. I was wondering, a lot of the, speakers before you have talked about how these will be, spectacular images, and I certainly am looking forward to seeing them. I was wondering, in general, if, the average person would be able to sort of see the difference between these images, maybe like sharpness and clarity compared to other previous images, even, Hubble's, quite famous deep field images.
I can have a go at that one. The real difference is the new information that we learn from these images. In comparison to Hubble, Webb does go deeper, and it is certainly sharper at the infrared wavelengths where there is overlap in the capabilities. But where the big dramatic difference visually will come is at the longer wavelengths, especially the mid-infrared instrument, in comparison to the Spitzer Space Telescope, which is also a predecessor to Webb. Webb is much sharper images than Spitzer for the mid-infrared. We're bringing the universe into high definition in the mid-infrared. And but in terms of the visual appeal of the images, it's going to be people who like looking at Hubble images are going to like looking at Webb images. The real difference is the new scientific information, and then really opening up the longer wavelengths, the infrared wavelengths, in a way that we've really never seen before.
Thank you. Do we have any other questions in the room? All right.
Hi, Nadia Drake with National Geographic again. We've heard a lot about some of the first images being of colliding galaxies, starbursts, stardust, the deep field exoplanets. But what about our own solar system? Will there be potentially an image of something much closer to home in that first release?
I think the answer is in the summary I gave of what will be in the packet.
I will follow up that Eric earlier mentioned the early release science, which is different from what's coming out on July 12th. Early release science are programs that have been selected, peer-reviewed, and planned for the first few months of Webb observation. And there is an early release science program that is concentrating on Jupiter and Jupiter's moons and the Jovian system. And so if we don't see anything within our solar system on July 12th, we will certainly see the planets very soon.
Thank you. Do we have any more questions in the room before we go to take some from the phone lines? Oh, go ahead.
I'm Yusuke Tomiyama, the Yomiuri Shimbun correspondent. So I'd like to ask you simply, so how many images will be released on 12?
How many images?
How many?
How many total?
That might be a question for you.
Yeah, so the final, again, because the team is, processing and working through the data, that final package will have all that information on July 12th. You'll see it in just a couple weeks. Thank you. Okay, we can go ahead and take some from the phone lines now. So I'd like to ask our operator again to give those instructions to ask a question and take our first question from online.
Absolutely. If you would like to ask a question, please press star one, unmute your phone, and record your name. If you would like to withdraw your question, you may press star two. Our next question is going to be from Marcia Smith of spacepolicyonline.com. Marcia, your line is open.
Thanks so much. My question has to do with Hubble, actually, and I'm wondering if anybody there can give an update on Hubble and how much longer it's going to be operating, because I remember that there was a goal to have Hubble and Webb operating at the same time. So if someone could sort of give an update on Hubble, and do you think that Hubble will still be operating when Nancy Grace Roman is operational? I'm curious about sort of the interrelationship amongst these telescopes. Each of them has their own merits, but if you have all of them able to look at targets simultaneously, how does that help the science?
I'll go on this one from the headquarters perspective. This may sound like an unusual way to go at it, but we have to submit 5-year budgets every year, and we just submitted our 5-year budget for Hubble. So we plan to have Hubble operating the whole time that Webb is operating. And if Nancy Grace Roman stays on schedule, there is a possibility that all three could be operating, which would be absolutely fantastic. Now, the need to do simultaneous observations, while for some programs that would be important, for many it's not, but just having data from Hubble and Webb about objects tells us very different things. They're looking at different parts of the spectrum, and that is, astronomers need those data to make additional discoveries.
I'll maybe jump in and give the scientist perspective. Scientists would love to have all three telescopes working at the same time because, as Eric said, they do have different capabilities, and ideally, as each one makes discoveries, we'll want to point the other two at the same targets. In terms of the synergy between them, Roman especially is a discovery machine. It maps very large areas of the sky, whereas Hubble and Webb go deep on individual targets or smaller areas. So that in particular would be a whole lot of fun to see the very rare extremes of the universe that Roman will discover and then look at them in the optical and ultraviolet with Hubble and in the infrared with Webb.
Okay, thank you both. We can take our next question on the phone.
Our next question comes from David Curley of the Discovery News. David, your line is open.
Discovery Channel, thank you very much for taking a question. You mentioned that you had the first year mapped out. With only 10 years, I'm assuming you had a good sense of what you would do over what the expected life of Webb was going to be. Now with the fuel savings and doubling the life, what does that mean for science? What are you dreaming of? What will you be able to do that you didn't think you might be able to do with a 10-year lifespan?
So every year we are going to have a call for proposals, which is how we plan out the next year of observations. So while we have the first year, the cycle 1 observations ready, it actually is 10,000 hours, so it lasts more than a year. And then next year, in February or so, we'll probably have the plan for cycle 2. Because of the 20 years, scientists are extremely excited. It allows them the opportunity to plan things where if they can get observations now, then you can do follow-up observations later. I will speak to my own program because it's something that's closest to my own heart. I'm looking for planets around small dead stars called white dwarfs. And if I can find them now early on, because of the time scale, having that long baseline for Webb, it means that I can follow them up in 5 years' time and actually really confirm that they're truly exoplanets if I find them there. So that's just one example. So it allows you to do things like that. I'm sure other scientists here have other science cases like that as well.
Great. Thank you, Susan. Our next question from the phone.
The next question comes from Gina Sanseri from ABC News. Gina, your line is open.
For someone sitting at home with an iPhone who walks outside and snaps a picture, can you put in really civilian terms what it takes to decide what to take a photo of or the data and how it gets to Earth and how it is processed? What the turnaround is on that?
Yeah, I mean, I can talk to that, say, from the first images perspective. It varies, right? So the images have been planned for a long time. There's been a lot of work going into simulating what the observations would look like so that everything could be configured just right. But once you know that, it's only a few days to plan things out, upload them to the observatory, take the data and get them back down on Earth. And then you have another long period of time where you have to spend processing the data. Right? This is not just snapping a picture on a phone. When you get the data down, they don't look anything like a beautiful color image. They don't hardly look like anything at all. It's only if you know as an expert what to look for that you can appreciate them. And then when the data are processed, the color images over a period of maybe a couple of weeks, essentially emerge in their full glory. So it's quite a process to watch.
Thank you. We can take another question from the phone.
Our next question comes from Bill Harwood from CBS News. Bill, your line is open.
Thanks very much. I'm wondering, when did the early release observations, the actual data collection begin, and how did that fit in with your test of the different observing modes? In other words, I assume testing was going on while you were collecting images with one instrument versus testing another. When did it start, and how did all that fit together? Thanks.
I can take it.
I can start it anyhow. You can add in if you'd like. So we have already started taking some of the early release science observations. There's different programs amongst the early release science programs, each covering different science areas. There's about a dozen. And each one exercises a different set of modes. But those are the first science observations. We've already used commissioning to determine that we're ready to take those science observations. And so we're only started now those where the mode has been determined to be ready for science operations. Is there more to that question?
Because we're going to see on the 12th when that process started and how that fit into the other checkout modes. Thanks.
Yeah, so for the first images, we started taking data a couple of weeks ago, and we're still taking data. We haven't taken all of them yet. And you're right that it was a process that was tightly linked to the commissioning activity, where we would only start taking data once the different instruments and the different modes were deemed ready for science, one at a time, as you have been able to follow on the Webb. And so that has driven a very, very interesting and tight schedule for us, right? So it's been exciting. Now instrument, now mode is ready. Now we can start to take data. So yeah, over the past couple of weeks and going into the next week, we're still taking data.
Thanks. We have time here for one more question that we can take from the phone.
Our next question is from Deepthi Bhathini from ABC. Deepthi, your line is open.
And if you are speaking, you are on mute on the phone. Okay, not hearing anything, so maybe we can go to our next question on the phone.
Our next question comes from Songju Kang of GNSM. Songju, your line is open.
Thank you. This is Songju Kang, and I work as a science communicator in National Science Museum in Korea. Congratulations to all the researchers who took part of this project first. And by what criteria were these initial pictures has been chosen? I mean, the initial package, what criteria were they chosen? Thank you.
Criteria for the original, the first images.
So the images were chosen to highlight the science capabilities of Webb, but also to produce spectacular color images, right? So to produce something that is akin to what we're used to from Hubble, which is slightly different. There's some overlap, but it's slightly different than what you might do if you just want to do science. So it's really looking at what the options are, looking at what Hubble did, but also looking at what the Spitzer Space Telescope did, which operated much, fully in the infrared, looking for objects that would produce a nice frame, a nice motif, have structure, have color, and then at the same time highlight science.
Great, thank you, Klaus. And so that is all the time that we have for questions during this segment as well. So thank you very much to our panelists and all of our speakers for being here again. Before we move into our final segment, we are going to take a short break of about 5 minutes for those in room to stretch their legs. So on the phone, you will hear hold music until we return, and we'll be back in 5. Thank you. All right, so we will pick back up here with our final segment of the briefing where we will hear more about Webb's commissioning process as we approach the start of science operations. So with us, we have Bill Oakes, Webb Project Manager at NASA's Goddard Space Flight Center, Lee Feinberg, Webb Optical Telescope Element Manager at NASA Goddard, Mike Menzel, Webb's Lead Mission Systems Engineer, also at NASA Goddard, and Charlie Atkinson, Webb Chief Engineer at Northrop Grumman. So once again, we'll hear from each of our speakers before we begin taking questions. So go ahead, Bill.
Hey, thank you. Like Lisa said, my name is Bill Oakes. I'm the project manager of JWST. I want to start out with really the last 6 months have been truly amazing. It's only really been 6 months and a couple of days since we launched. Really, to me, it doesn't even seem that long ago that I was sitting on console on Christmas Day waiting for that launch to occur. But during that time frame, as you've already heard, and the last time at least I participated in one of these big press conferences, we had just finished deployments. Deployments went very smooth. That was to me, the most stressful part of the commissioning because everything had to work and went through so many of our single point failures and mitigated those at that point in time. But since then, we verified the rest of the spacecraft. The telescope alignment was completed, and now we're zeroing in on the end of the SI commissioning and the wrapping up of all our verification of all our science modes. Like I said, it's been an amazing 6 months. But when you go through commissioning truly is a learning process, not just a verification. Anytime you launch any spacecraft, every spacecraft has a very unique personality when it gets on orbit. There are unique things about it that no matter how much ground testing you do not learn until you actually get on orbit. And we had those experiences. We went through I think we had somewhere on the order of 6 or half a dozen or so safe haven events. That's when the spacecraft saves itself. They lasted no more than a couple of hours to a couple of days. I think I totaled up the time, and it was about 4 days time we spent in safe haven. Most of those were all oriented around the attitude control system, which is very typical. I worked Hubble commissioning. Believe me, that was a whole lot more safe modes and spent a lot more time going through that process. So this was still, for what has complex as a spacecraft as we have, the fact that we spent maybe 4 days or so in safe haven total was miraculous. That really is part of that learning process, and that learning process will continue even after commissioning. And as the spacecraft ages, we tend to still learn more about the spacecraft. As you've heard, and you've heard a lot about commissioning already, but by the end of this week, we will have formally verified 16 of the 17 science modes. We'll really only have one commissioning activity left that should finish up by about the middle of next week. And then in a couple of weeks, we will have our final review that will basically say we're ready for operations, even though we are already going into operations. This kind of formalizes that decision that, yep, we're ready to move forward. I do want to take this moment to express my gratitude as far as a project manager and a leader of this team goes. One of the first things you learn is that you need to express gratitude, and I want to express gratitude publicly. This is an amazing team. We've spent probably 20 years building this telescope. We've estimated on the order of about 20,000 people have worked on the Webb telescope around the world. During that time frame and during my 11 and a half years, so I'm still kind of like a rookie on this mission, and many people have already been on it over 20 years. One of the things that I have learned is the diligence, dedication, and sacrifice this team is willing to make this mission successful was nothing compared to it that I've seen in my career. And I always take an opportunity to thank not only the folks that worked on the mission, but also their families and their friends, pets, significant others, whoever provided them support at home, because without that support, they can't do their job to make Webb successful. And then finally, personally, it's really been an honor and privilege to work with all these folks. I've gone around now and talked to some of our major contractors, thanking them. And I tell them all the time that we will be bonded forever by the experiences that we've had from Webb. We can get together 10 years from now. We could have been doing something totally different, and we will still have that connection. And so I just wanted to take this opportunity to publicly thank everyone. You can't single out one individual. I appreciate the kind words that Thomas said about me before. But there is no one individual who made this mission successful. It was a team effort all along, and it was not just a NASA team, it was a NASA industry, academic, and international team that made this successful. Thank you.
Okay. Hello, everybody. I'm Lee Feinberg from Goddard. I've been the telescope manager for over 20 years. Now that the telescope is aligned and we've now characterized it, I thought I would share a little bit with how well it's performing. We haven't given a lot of numbers in the past, so I'll give you a few, and I'll try and not get too technical. But the main one is, we set out to build a telescope that is what we call diffraction limited at 2 microns. And what that means is that diffraction limited means that you are only limited by the laws of physics. It's actually the laws of diffraction, which affect how well a telescope can image. And if you build a perfect telescope, you will only be limited by the laws of physics and not how good the mirrors are made and not how well you align it. We just went through this alignment. So our goal was to be diffraction limited at 2 microns. That was kind of the quote requirement. At this point, we feel that we're operating at about 1.1 micron, which is almost a factor of 2 better than we set out. And what that means is we have quite a bit of margin in terms of the optical performance. And we designed the system to have margin. I think we have even more margin than we anticipated at this point, which I think is really good news. And it's also good news for the science that people will be doing, because the shorter the wavelength that you're diffraction limited, the higher the quality the images, particularly in the shortest wavelengths. So, for example, in the near-cam shortwave channel, the performance all the way down to 1.1 micron is as good as the laws of physics allow. In terms of other optical parameters, pretty much across the board, we're extremely happy. We check for things like we call it vignetting, which are any blockages in the light paths. We don't see any evidence of that. The throughput of the system is at or better than we expected. And we don't see any signs of contamination or ice. And ice actually in a cryogenic system, especially a large telescope, is really critical, because when you first get in space, anything that's warm is outgassing water, and we had to use heaters, and a lot of what we went through in the first month was managing to make sure that we don't form ice. And one of the reasons you don't want to form ice is if you form ice on mirrors, then when you do spectroscopy of things like exoplanets, you detect the ice on the mirrors. So we worked really hard on that. I think we put on the blog a couple weeks ago that we've had 5 what we call measurable micrometeoroid impacts. These are ones that we can actually measure with our routine wavefront sensing control. So every couple of days, we're making measurements. And so we could actually sense these. And if we can sense them, we can also, as part of our routine adjustments, make adjustments to essentially remove as much of it as possible. And so very fortunate to have 7 degrees of freedom, 6 actuators plus the center one on each mirror, which allows us to do that. The last of these impacts, as we mentioned, was larger than the previous one, and we think that's because of just the statistical distribution in the size and the energy of these kinds of things. We're continuing to look at this issue, but what we're mainly focused on is just operationally trying to minimize the effects so that we use as little of that margin I talked about before as we can. But the numbers I quoted already include the ones that we've had, and they're really negligible. And so this is more of an issue about how do things progress over a long period of time. We have completed also our thermal stability test. I think some of you heard about that at one of the previous ones of these. And what we did is we actually soaked at a hot attitude initially for 4 days, and then we flew the telescope to a cold attitude, so almost worst case hot to worst case cold, for 8 days, and then slewed back. And that's a really critical thing, because stability is really critical for the scientific performance. And Webb is designed to only realign those mirrors every couple days, not continuously. Some ground telescopes have continuous operation. So it was a very challenging, I would say maybe the most challenging part of the telescope. I'm looking at Charlie, because Charlie was the deputy telescope manager for Northrop Grumman for many years. And I would say we worked harder on the stability issue, designing, building, and then even when we tested the telescope, we even found some stability issues that we had to fix. Well, the fix completely worked. Our stability estimate for what we call thermal stability was 17 nanometers. A nanometer is a billionth of a meter, and we hit it within 1 nanometer. which is truly remarkable for a 6.5 meter cryogenic telescope. Our allocation is 54 nanometers. So again, we have a huge amount of margin on stability. These are phenomenal numbers, and they're going to directly impact the quality of the science. The other number that's really impressive is what we call the line of sight motion. We have a loop between the fine steering mirror and the guider. The guider is the Canadian contribution. We close that loop about once a second to keep things very stable. And we're finding that we're typically running 1 to 1.5 milliarc seconds, which is about a factor of 2 better than we allocated. Hubble, for example, typically runs at 7 milliarc seconds. So we have outstanding line of sight motion. You combine that with the thermal stability and the image quality. You combine that with the thermal stability and the static performance, and that's what goes into that image quality I mentioned, the 1.1 micron diffraction limit. All of that is included. So this is an outstanding optical telescope, and we're very proud of it. And as Bill said, there's too many people to thank. It's been a huge, amazing team. The team has changed. I was out at Ball Aerospace last week, and we had some of the folks who helped make the mirrors 20 years ago, and it was amazing how everyone along the way has just followed our progress. And this last team has been just as amazing as the first team. And I think this is all just really a sign of just how hard everyone worked and how careful they were to all the details.
Is this, okay, I guess this is on. Okay, well, I'm Mike Menzel. I'm the Mission Systems Engineer for James Webb, and I have been on this job for about 24 years, 25, almost 25. As folks have said, we've completed all the major commissioning activities. We've demonstrated most, if not all, of our mission functions and capabilities. And among these are our 50 very complex deployments that retired 295 single-point failures. 295 ways that this mission could have failed. We've gone through 3 successful mid-course corrections, 4 successful station-keeping maneuvers, 14 momentum unloads. And it was the excellent injection accuracy of the Ariane and the timely completion of our mid-course corrections that led to this extremely excellent propellant reserve that Dr. Melroy had talked about earlier in her presentation. With all this success, I've spent the last couple of weeks answering micrometeoroid questions. So I'll just say a little bit about that here. Lee's already described the observed impacts on our primary mirror. Now, we worked with the Marshall Space Flight Center early in the design phase of James Webb. We knew that micrometeoroids were going to be something we'd have to live in. So we did predictions. We used micrometeoroid models to predict our environment and help us. That informed the way we designed both the telescope and the sun shield to make sure that we could live in that environment. Lee said that the first 4 impacts, the first 4 of the 5 that we've encountered with this, have been in family with those predicts, both in their frequency and in their impact on the primary mirror. The models had said, hey, on the average, you'll probably see about 1 impact a month, and that's about what we've seen. It was the last impact that just had a little more influence on the telescope than we had predicted. Now, these predictions are statistical in nature, so you're not going to get definite answers from them. So time will tell whether or not that last impact was just a kind of anomaly, or whether it should be more along the lines of expectations. But one way or the other, the telescope, even after that last impact, is working, magnificent. As Lee said, about 2 times better than we thought. Going forward, we have strategies, and we're still formulating some strategies for the micrometeoroid environment. And the micrometeoroid population has 2 major components. And we're formulating strategies for each of the 2 components. The first one, we call them sporadics. And this is like the pervasive stuff that's in our solar system. Our planets go through them. Our Earth orbits around them. And much in the same way as a car driving through a rainstorm, in the direction that you're traveling, the meteors and or the raindrops seem to hit you from that direction. So we're looking at whether or not what we expect of these sporadics is in line with what we predicted. If it's not, we can come up with strategies maybe to avoid the frontal direction of our motion on that, but we're still not at that point. And then there's another component of the micrometeoroids left by recently by comets that dive in, loop around the sun, and go out. They leave a trail of debris they leave a trail of debris after them, and the Earth and James Webb will periodically go through these trails of debris called meteor showers. And we can predict their times and the directions that these come from, and we can also predict whether or not they're significant showers or not. And if they are, we can orient the telescope such that the mirror and the sensitive portions are not, can avoid those directions. And I also want to remind people that NASA has been dealing with the micrometeoroid environment for its entire history. We've even put, astronauts go out in this environment, so we have some pretty good success in predicting these things. And then just to sum up, meteors aside, the mission has been excellent. We've had a couple of anomalies, but they've all been solved actually within hours. It's been kind of gratifying and surprising that we've trained for all these many years. We've trained under some ridiculously worst-case scenarios, and it's been gratifying that every time we've seen an anomaly, probably within 1 or 2 hours, we figured it out and we're well on the way to recovering from it. With that, I'll pass it on to Charlie.
Cool. Thanks, Mike. Charlie Atkinson, Northrop Grumman. I'm the chief engineer at Northrop Grumman for JWST. And as Lee alluded to, prior to that, I was the deputy telescope manager. Been working on the program for about 24 years. And to me, it's incredibly amazing that we are on the verge of handing this incredible performing observatory over to the scientists, for them to be able to make observations and discoveries that, I can only begin to imagine. But we've got this tool that they can now use to uncover things that, we don't even know how to ask the question of right now. And to me personally, I think that's fantastic. Mike and Lee talked about the micrometeoroid environment. I think Mike tried to do a good job of conveying this isn't a surprise, right? We know about the environment at the second Lagrange point. We have lots of data about what it's going to be like. And the entire observatory has to perform in that environment. The sun shield, as Mike was talking about, we did testing very, very early on to understand what the effects of micrometeoroid bombardment on the observatory would do, and what the performance would be, both nominally and over time as we see micrometeoroid hits. And that's all planned for. That's where we have margin. That's why we're seeing incredible performance today. We've got that margin available to us if things start to slowly degrade, and we expect them to, like we would for any other mission. And for me, as an engineer, having worked on this for as many years as I have, it's incredibly gratifying to see the incredible performance that Lee talked about of the observatory. That 1.5 milliarc seconds of line of sight stability. That's like if you go to the moon and you paint a target that's 10 feet in diameter, you'd hit that better than 9 times out of 10. Seth Curry can't do that. Sorry, Seth. No offense, man. It's also like sticking a silver dollar on the luggage bag return at LAX and hitting it better than 9 times out of 10 from here. Absolutely incredible. The 17 nanometers of stability that Lee talked about, 17 nanometers, that's 170 angstroms, 170 hydrogen molecules. That's how much this telescope is changing by. 6.5 meters in diameter. That includes the effects of the mirrors, the actuators, the structure behind the mirrors, the cabling, the thermal control system, the hinges and latches, everything contributing 17 nanometers of distortion. The other thing that I've always looked at that has always piqued my interest in terms of performance of the observatory is the temperature on the cold side. The job of the sun shield is to reject the heat from the sun and prevent it from warming up the cold side of the observatory. And the way that we determine whether that's working or not, by looking at the temperatures there. And to me, the one big indicator is the secondary mirror, which is sitting out in front of the primary mirror. Its main contribution to its heat is directly from the sun shield. And it's sitting there at 29 Kelvin, 29 degrees above absolute zero, colder than we expected. So again, giving us better performance than we expected and margin to be able to use if we need to. Absolutely incredible performance.
And then Lee talked about the pointing stability and changing the orientation of the observatory and monitoring how it changes over attitudes. The fact that the temperatures change as expected, and we're seeing the performance as we expected or better than expected, is incredibly gratifying. And then finally, we've spent, as Bill alluded to, the last 6 months getting ready for turning the observatory over to the scientists and making sure that every subsystem on the observatory is ready for science operations. So the communication system that gets the science images and the telemetry, engineering telemetry down to the ground, takes the commands up from the ground. Command and data handling system that takes those commands and routes it out to the different subsystems. Also collects the science images and the engineering telemetry and stores it until it's ready to be downloaded. The power subsystem. I remember Christmas morning watching the launch of the observatory, and that camera that was on the upper stage of the Ariane 5 capturing the deployment of the solar array. That was unbelievable. Yeah, we got power. And then conditioning that power and sending that out to the rest of the observatory. Absolutely fantastic. The propulsion system that enables us to do the station keeping and the momentum unloading that Mike talked about, that's all working fine. The attitude control system, which enables us to go from all the different pointing in the field of regard of the observatory and to enable that, really incredible line of sight stability with the nested control systems that we've got for pointing control. And then the actuator and telescope alignment capability that our friends at Ball put together, using science images to interrogate the performance and determine the alignment of the telescope, and use that information and then tell us how to adjust the 132 actuators on the mirrors to get the performance peaked up as good as Lee described it earlier today. And that system is all working perfectly, and we know it needs to work well because we know now that it's going to be needed to make adjustments after we see meteoroid hit. So again, I'm incredibly excited. I cannot wait for the science that's going to be coming out on the 12th. I can't wait for the science that's going to be coming out for the decades to come.
Great. Thank you all so much for those updates. Once again, for our last Q&A segment, we can start with those in the room before we go to the phone lines, although as a reminder, it is *1 if you're on the phone to ask a question. So we can go ahead. Are there any questions in the room?
Jeff Faust of Space News. For anyone on the panel, hearing a lot of comments that the telescope's performing better than expected. Any sort of theme, any sort of common cause why the telescope in general, whether it's thermally or optically or whatnot, is exceeding those expectations?
We'll let Mike answer that.
Well, I think we'll go around the panel here. Part of it was Bill's alluding to me because as a systems engineer, I made sure that we had performance margin that we can count on. And as Lee had mentioned and Charlie had mentioned, for instance, when it came to what we call jitter, we had a spec to be good to 7 milliarc seconds. And if you want to know what that is, put the telescope at the Capitol, put a laser pointer on it, and you can keep that laser on a penny on the Empire State Building. That's 7 milliarc seconds. Well, we're performing at 1 milliarc second. So we made sure that we had margin in our performance that now we are actually leveraging. And now I'll turn over to Lee and to Charlie to add to that.
I mean, I would say, I always say to people, attention to detail. The attention to detail by the team. I mean, we knew how significant this observatory is. This is the biggest, most complex science mission potentially, that NASA's ever built. We knew this was we knew we had to have attention to detail. And the second thing is there was a real emphasis on testing. We tested everything that we could think of. There was a lot of lessons learned, including from Hubble, in terms of how the transparency that we had with that data, the level of review we had. And we did find things along the way. I mean, where we actually had to change designs, including, we put something on a shaker table and we saw some, vibrations at frequencies we didn't expect. We put dampers on it. the late optical testing that we did, where we changed the thermal insulation around the primary mirror. So I think it was kind of a combination of just a lot of detail and a lot of testing. I don't know, Charlie.
Yeah, the only other thing I would add is we talk about the requirement being diffraction limited at 2 microns. That was with a 95% confidence. So we had to be 95% confident that we were going to be diffraction limited at 2 microns or better. So the chances that we were going to be better was quite high. So the fact that we are doing better isn't that surprising. It's just incredibly rewarding, at least from my perspective.
All right, great, thank you. Do we have another question in the room?
Hi, this is Islam Ahmed from Agence France Presse. Sorry, you might have already spoke to this, but could anyone on the panel sort of analogize a little bit what we mean by stability of 17 nanometers of distortion? If you could sort of draw that out a little bit, or diffraction limited at 2 microns. I'm sorry if it's repetition.
Well,
sort of lay terms, you know, like to.
Yeah, I mean, so what stability means is literally, you could think about those 18 primary mirror segments. As we flew around the sky, things change temperature. And if you're not stable, things are going to literally tip and tilt. And so that beautiful mirror is no longer going to be beautiful. It's going to be, you know, it's going to have a funky shape to it that's not going to make a nice, pretty-looking star look like a pretty-looking star. Stars that will start to become blurry if there's too much of this. We call it instability. And so that's really what we're talking about, is across that 6.5 meters, how stable are everything. We also do care about the stability of the mirrors, each individual mirror. We were always a little less worried about that because we chose a material, beryllium, which at these temperatures, if you look at its material properties, it's incredibly stable. So the challenge for us wasn't so much to mirror the individual mirrors, but it was from one mirror to the next. And if you think about those mirrors being attached by a large composite structure, mounts, cabling, all of those things from one mirror to the next are participating as temperatures are changing. And we can't allow this to happen. We're trying to keep it stable like that. I don't know if that's helpful.
Thank you. I don't see any other questions in the room at the moment. Oh, do we have one up here? Okay, no, I don't see any in the room, so we can go ahead and take some from the phone lines. I'll turn it over to the operator for those.
Great. Our first question comes from Alexandra Whitsey. Alexandra, your line is open.
Hi, it's Alex from Nature. Thanks for taking my call. If I can just remind everyone to please identify yourselves. Those of us on the line don't have visual cues to identify the voices. That being said, I think this question is for Mike. It's about the micrometeoroid environment. So number one, you all have publicly talked about having seen 5 impacts, the 5th being the biggest. Have you seen 6 or 7 or 8, any more since then? And then the second part to the question is about, you were talking about how the environment, the micrometeorite environment is known quite well. Does NASA really have a lot of data about what things are like at L2? I mean, there haven't been that many missions at L2, certainly nothing of this size. How different is the micrometeoroid environment at L2 compared to other environments in which NASA often operates space telescopes?
Okay, yeah, for the first question, I don't think we haven't detected any more impacts after that 5th. And when it comes to the L2 environment, the differences between that and the Earth, we have a couple probes out at L2. ESA actually has one, and we're trying to get data from the Gaia spacecraft, and ESA is providing us with that. But so far, at least a cursory look at what I've seen, it really doesn't look that out of family of what we predicted. And the micrometeoroid environment, the difference between L2 and the Earth, theoretically really shouldn't be that different. And if you think of things, if you picture the solar system, the Earth is 93 million miles away from the Earth. Well, let's round that to 100 million. L2 is only 1 million miles away from that, so it's only 1/100th the distance. So, theoretically, the difference between those environments really isn't expected to be that different. And in fact, I will point out too that the environments, the debris environment, both natural and man-made near the Earth, is actually worse, most likely worse than that at L2. Not only because of man-made debris, but because there's a gravity field from the Earth that's kind of pulling stuff in and trying to focus things and concentrate things. So, we have some limited data from L2 spacecraft, namely Gaia and a couple others that are out there. But theoretically, we don't expect the L2 environment to be much different from the Earth. And in fact, theoretically, there's arguments to say the Earth environment might probably be quite a bit worse than L2.
Thank you. And for those on the phone, that reply was from Mike Menzel. We can go to a next question on the phone.
Our next question comes from Bill Harwood. Bill, your line is open.
And Bill, if you are speaking, you're on mute.
Oh, sorry about that. Yeah, I don't know who this is for, but it's a simple question. I was going to ask, in a typical 24-hour period, when you're doing normal science ops and everything's checked out and commissioned, how much time is spent on actual observations versus housekeeping? Like you were mentioning, you check the alignment of the mirrors, things like that. How much time is spent on those kind of housekeeping chores? Just to give you some sense of how that works. Thanks.
We have a specification for that, and this is Mike Menzel, by the way. We're expect to be 70% efficient, meaning over the average over the course of our lives, we would be collecting science photons for 70% of the time. The other portion of that time would be the major overhead type of operation of the observatory, is that of slewing. Moving from one place to another, we do that relatively slowly. We move about 90 degrees in about an hour. But for the most part, we're required, and we can easily meet an observing efficiency of 70% with this observatory.
All right, thank you. Okay, well that is, we're approaching the end of our time here, so unless there are further questions in the room, we will go ahead and wrap up this segment. So if you had a question that we didn't get to in one of the earlier segments or, a follow-up, please reach out to us, and NASA's media team will be happy to help with those. And thank you again to all of our speakers, to those who joined us by phone, as well as in the room here in Baltimore. And to learn more about how you can join us or cover the release of Webb's first images in just 2 weeks on July 12th, please visit www.nasa.gov/Webb. So thank you very much.
Thank you.
That concludes today's call.